Hi everybody, my name is Oskar Eriksson, customer-facing data scientist at DateRobot based in Stockholm, covering the Nordics together with my colleagues here. It's great to have your attention for a while we talk about green machine learning or green AI, if you'd rather. Uh, Sorry, I have a bit of a cold, hence my voice, but please bear with me. This is the agenda for today. We'll talk about the differences between red and green AI. Sorry, the theories that sort of make up the fundament for this, so that we'll understand how we can shift from red AI to green. And we'll talk about how to achieve this in DataRobot. I work at DataRobot, so pardon me, but I'm sure that whatever type of platform you're using for machine learning or AI, you'll see how to apply what we're talking about here today in your reality. And then we'll talk a bit more on what we can do outside of modeling, perhaps, to move from red to green. So what's the problem? Well, as the title says here, the model accuracy has increased, especially in deep learning, but in any type of machine learning, really, in the past decade or so. So on the left-hand side, we see on the x-axis we have year, so sorted on time, and y we have the petaflops per day for training the model. So petaflops per day for training is basically the amount of calculations required to train the model per day. And we can see that it has sort of been linearly increasing between 2012 and 2019. These are mostly deep learning models, and that's the easiest way to sort of understand the size of this problem, because these models are so big and complex. It still applies, but to a smaller extent on more simple, less deep, more shallow models, so to speak. And what does this mean then in terms of something that we can understand better than that we just see that it's an increase and that it's more computation is required today than before? Well, we can say that this neural architecture search, the NAS model here, also a good wrapper, that costs approximately 626,000 pounds of carbon emissions to train from scratch. So what is that? That's like 300,000 kilos. It's quite a bit. That's actually more than 17 times more than what the average American human does in 1 year. So to train this one right here, so let me get my pointer out. It's more than 17 Americans. And you know how Americans are with their huge cars and their meat consumption, etc. Also, the cost of it in terms of money, so that's another aspect of green, right? It's not only about the environment, the color of money is also green. It costs sometime between $1 and $3 million to train in a cloud environment. That's also quite a bit. It's not on this slide here, but maybe you heard about the natural language processing model, BERT, that costs approximately 1,400 pounds of carbon emissions. So what is that, like 600 kilos or something, which is 4% of what the average American burns in 1 year. Well, that's still quite a lot, but I think that many of us have run into BERT and would like to use BERT to some extent. Just make sure that you try to avoid to train it from scratch, or someone may come to you with a cloud bill that says that your from scratch training of BERT costs $4,000 to $12,000 approximately to train. Yeah, so that's something. One needs to remember also that maybe you get your power for your infrastructure from renewable source, so you think that, well, why should I care? This is green anyway. But then you're using renewable resources in something that you perhaps didn't need to spend it on, and these renewable sources could have been used more wisely by someone else who needed it. But also it means that you need a lot of money, a lot of resources, a lot of infrastructure to train cutting edge models. And that can really make innovation stale. That's not ideal at all, actually, because then it means that only people who work at the very big tech companies and some super secret government agencies will be able to innovate in this space, unless we start to consider other things than just model accuracy as well, which brings us to the right-hand side of this slide. So if we, instead of looking at the time, we compare the millions of floating point operations, that is computations required, and then we plot it by accuracy of some different models within computer vision. We can see that the NASNet is the most accurate one, along with the SCNet, but they require a lot more computations than these models to the left-hand side here. So if you just went for accuracy, you would end up picking one of these, even though they require a lot more power to train. So one important thing to remember is that red AI is when you purchase better results just by adding more compute. You make the models bigger, essentially. What we need are new metrics other than just accuracy. Some of them being efficiency. These have been cut from a report I read from Linköping University, or rather a master's thesis. And there are a number of efficiency metrics that you can consider. Roughly speaking, we're talking about the energy required to train the models, training time, training energy, but also at inference times when you're actually making predictions. So all of these are different ways of measuring energy efficiency, which is how much useful work did you get done and how much energy did it require to do so. And that can hopefully give us in the end green AI, so accurate and efficient machine learning. If we take this plot that we saw on the previous slide and then we just see how many points of accuracy we get per billion floating point operations versus model, then we'll see that SCNet and NASNet, which are the most accurate ones, are actually the least efficient ones with this metric. And if we instead look at FENet, which you see right here, it's very small actually compared to the others. It's not the most accurate one. It's at perhaps 75%, whereas the others are at more than 80. So that would give you more bang for the buck, so to speak. But that also depends on how valuable accuracy is to you in your use case and what you're doing with it. So how do we maximize efficiency in machine learning in general then? Well, Schwartz and his friends from the Allen Institute of AI in the state of Washington somewhere, I think, they propose in one of the articles that the cost to process a model is a function of that the result of it grows linearly with the cost of processing a single example. So that's when you have the neuro data, what it needs to go through to actually end up in a prediction or some type of result. The size of the training data set and the number of hyperparameter experiments in it. This gives us some way of separating the different means we can take. Well, as stated, E as a single example, a raw data and observation needs to pass through parameters in the model. So one way to reduce this is to use a smaller model with fewer necessary parameters, both in training and in scoring. And a lot of people like to play with deep learning, and I myself have been guilty of doing so, even in use cases that don't really demand it. Sorry, my bad. So just think about that first. They are harder to tune, deep learning models. They require more computation time often, and you can get a very long way with boosted trees and other approaches. D as in size of data. So more data normally increases accuracy, but the marginal contribution decreases quite quickly. Anyone who comes from the world of statistics will know that after a few hundred observations, your confidence intervals will become very, very small, and you know what impact that has on statistical inference and statistical substance for that matter. But don't use too much data just because it's available. It might be that more data might actually hurt your models, because normally you have to go further back in your history, and that data might actually be irrelevant to you. So make sure that you use the right amount of data for a problem. Filter out as much as you can before you start modeling. And if you have classification problems or zero inflated regression, make sure to downsample. I mean, if you have a 90% majority class in your binary classification problem, and you still have a lot of data, you can adjust that quite a bit so that you move from having 90% of your majority class to perhaps making it a 75-25 split or whatever, so that you use fewer rows, but you'll still get accuracy that is equally good. And that's super easy to do in DateRobot. We'll have a brief look at that in a slide. So don't use all your available data before you know which model is likely to perform best. So start small, start with a sample. Use feature selection techniques, especially when you put your brain into it and start to think that what data makes sense to put in here, and to put in all of your data and then just shake your computer until it gives you some type of result. Well, you will get some type of results, but your model will likely be a bit overfit, and you will spend a lot of time and resources on it. Also consider file types. So CSV files are smaller than JSON, for example. It's not really my area, but there are a number of things to consider there. Age, as in hyperparameter experiments. So hyperparameters are tuned to maximize the predictive power of a model. So you can do that in a variety of ways. You can do it manually by just testing different combinations, changing one piece at a time. But that is normally quite difficult, especially if it's a type of model that you're not too familiar with. There are some automated techniques. Some of them test all different combinations of hyperparameters to sort of give you the optimal answer. They take a lot of time. They burn a lot of resources. But there are also other smarter methods that give you a very high probability of, if you use a lower amount of combinations, but you have some type of smart way to see which is the best way to go to minimize the error of this model, then you will run fewer iterations but get accuracy that is just as good. But don't waste too much time on hyperparameter tuning, because it's not really going to help you as much as finding the right data. And by finding the right data, it's not always about being able to connect to another database or reading another table from somewhere. It can also be as easy as finding a correct interaction effect in your already available data or something like that. So how do we measure and increase efficiency in DateRobot? For those of you who haven't seen this is the Winamp logo. Almost only Lightning I could find that looked cool enough. For you kids out there, Google Winamp. Those were the days. So DateRobot performs an exploratory data analysis. Well, it performs two exploratory data analysis, actually, one without the target and one with the target. And that reduces the amount of features that you use, because it removes redundancies. That decreases D, as in data. So here we have an example of a feature with 4 unique values. So you could say that it varies. It has different variance metrics that are positive, but more than 99.9% of them or something are equal to the value no, and the others are barely existent. So it's not very useful for modeling. So DateRobot removes that. It also performs a bunch of other checks that everybody should do. Smart downsampling lets you just with this slider here choose how much you want to downsample, and then you get a visual overview of the results from that. DateRobot builds lists for you that you can use for modeling, lets you add your own, also lets you find which features are representatives of clusters of features. When I say features, I mean variables or columns, or you use these lists of features for modeling, but you can also add your own reduced lists containing just the ones that you think make sense and that you have seen from results from previous models that they will be useful, etc. For all of our models, we have a variety of accuracy metrics. Up here we see log loss or binomial deviance, or whatever you want to call it, cross entropy perhaps. And there are many you can choose from right here. We have more in the evaluate tab, and then you can compare them to the data that you see here in the model info tab for all of our blueprints or models, such as the model size, the inference time, training energy on our cloud. And then we can get all of the ones that we saw from previous example, except for inference energy. So we have a lot of convenient stuff built in here. There's another discussion which of these metrics are best. That depends on your use case, but there's also a deeper discussion. Training time may actually vary depending on how busy your infrastructure is at the time of training. So maybe that's not the best metric, but you should do what's possible, not what's best in general, I think. We also show you the inference time efficiency as a built-in overview, where you can plot your accuracy metric against the time it takes to make 1,000 predictions in milliseconds to see if you have high accuracy and quick scoring time in some model. Can also see if more data is warranted to obtain a lower error. So here we have log loss on the y-axis, and the sample size varies over here, and we can see that if we increase the sample size, do we get better results? So have a close look at the axis here. It goes from 31 to 28, basically, meaning that, yeah, in this case, maybe more data is warranted. But it's not only about modeling, it's about project as well. So the entire workflow is a source of potential carbon emission savings, right? So if we started discovering problem definition, then find the right use cases that reduce your carbon emissions as an enterprise, and make sure that you don't just do good ideas that seem like fun. You need to make sure that you have buy-in from everybody who's supposed to be using whatever you build in the end, so you're not wasting resources. That's also another way to become even more popular at work, to actually do something useful, right? And make sure that you measure CO2 as some part of your KPIs. And for data preparation, don't explore and transform too much. Keep it at the right level. That's also a way to actually get started with modeling and not spend your entire life preparing and shaping and looking at data, which I think has happened to us all to some extent. But also find the optimal amount of data for the use case. There are different ways to assess that. In the model development area, so DateRobot can build models for you that are almost always good enough, and then you can further improve them or beat them, whatever you like. Avoid deep learning unless it's warranted. For some use cases, it's absolutely necessary, and there you should. And also make sure to automate feature engineering so that you find the combinations of features or processing of features that make sense for your data. As for analysis, insights, and validation, again, avoid deep learning, because then it's much easier to deliver insights and get your models validated so that they're actually used. Because if you do all the nice work on the left-hand side here and then you stop here because it's absolutely impossible to understand your models, then it's good to have some type of standardized means of communicating insights to everybody involved in the model building and validation. Also to keep the models as simple as possible, and also test some type of standardized documentation so that people can understand what you actually done. Because if you can't get your models trusted, they are not likely to make it into production. And in some businesses more so than others, of course. And then something that is extremely important here is to monitor model performance so that you only retrain models when you really need to do so and not whenever new data comes in or something, because that can help you from retraining models that require a lot of energy to run and also a lot of your time probably for you to manually validate that they actually work as expected. So monitor your models. Of course, DateRobot can help with that. And also minimize the amount of duct tape you need to integrate your models onto your existing infrastructure. So you need to make it easy to deploy and easy to set these things up so that you can work efficiently. At DateRobot, we eat our own dog food. We have actually done this on our own infrastructure. So we have always been very keen to deliver a great user experience. So it can't take too long time to run a DateRobot project, and it can also not. We can't have a bunch of models failing to run because we haven't allocated enough resources for them. So what we did first is that whenever we had a model run on our cloud, we would allocate memory and CPU and be very conservative so that we would be absolutely positive that it would not crash. But CPU and memory usage vary based on things like the size of the data set and the structure of it. So we took that data and then we predicted the resources we needed for a given job. And by doing so, we could reduce how much memory we allocated to each model, make it more optimal, and reduce the workload on the infrastructure, which is good for everybody and also for ourselves and our customers, because while maintaining a good user experience, we didn't have to sacrifice as much money on our cloud bill or energy on that. So to summarize, don't stare blind at accuracy, minimize ED and H, experiment state and hyperparameters. We provide a lot of functionality to help. Maybe whatever platform you're using does so as well. Don't retrain models unless you have to, and pick the right projects. How does that sound? Here are some resources for you to have a look at. You can test DateRobot for free. You can also connect with the peers on our community and on the other resources you find here to find solutions to whatever challenges you may have. Explore new use cases in our Pathfinder. You'll find how to do them, what's required, etc. It's really good. Join our community and have a look at what's going on there. Lots of in-depth discussions about the latest and greatest in machine learning and data science. And feel free to connect with me for whatever you'd like to talk about. Thanks a lot for your time today, guys.